Now I will do a second example of using power series to solve a differential equation. Here's the problem statement. Here's the differential equation. This means y. This y double prime means the second derivative of y with respect to x. Y is a function of x. All that equals 0. It's a second order equation, by the way, homogeneous. And we're only asked to solve through the x to the fifth term. When you characterize it or put it in standard form, you'd have x over x plus 2 equals p, and q equals -1 over x plus 2. We went through this in other recordings. So the singular points are roots of x plus 2 equals 0, which is -2. X equals -2. That's the one and only singular point. So 0 is an ordinary. So we can find two linearly independent power series solutions centered at 0 as the particular solutions to this equation. The radius of convergence is the distance from 0 to -2, which is 2. Always a non-negative number. So the interval of convergence is -2 to 2. Once we find the power series, that's where they'll converge, guaranteed to converge. Here's the power series. Y is going to be a power series. Its first two derivatives, we already went through this. Substitute these things into original equation. Substitute these sums. So this here is y double prime from here. This sum here is y prime. This sum here is y. So here's what we get after those substitutions. First thing we'll do is distribute what's in front of the sums into the sums. Since this itself is a sum, we're going to break this sum, infinite sum, up into two infinite sums. First one is x times this sum, which we bring in, which raises this exponent or raises this exponent by 1. So we'll go from n-2 to n-1. Then the plus 2. And everything else is the same as it was here. Now for this sum, we bring in this x, so we raise that power by 1. So n-1 becomes n. And minus, nothing was in front here. This is all the same. So now what we do is see where each sum starts, what power of x. N equals 2 means x to the 1. That's where it starts. N equals 2 here means x to the 0 in this. N equals 1 means x to the 1. N equals 0 means x to the 0. We want all of them to start at the same power of x. So we want to pull off this guy's first term and this guy's first term. So this guy's first term will be 2 times c sub 2 times 2 times 1 times x to the 0, which is 1. That term. This guy's first term is just c sub 0 x to the 0, or 1, or minus c sub 0. Minus. Pull those first two terms out. This guy will stay the same. This guy, because we pulled the first term out, the sum now needs to start at n equals 3. This guy starts at n equals 1, and this guy, because we pulled the first term out, he starts at n equals 1 also. So we can combine these two guys. They both start at n equals 1 and go for x to the n. So that's c sub n. They both have c sub n, n-1. So this one sum here is these two sums put together after I pulled out this guy's first term. And that sum now starts at 1. So now, after this step, we want to change the indices from n's to k's. I always set my k's equal to these exponents. So So this first guy, the k is going to be n minus 1, which means n equals k plus 1. So every n here I replace with k plus 1. C is k plus 1, k plus 1, k, x to the k. And when n equals 2, k equals 2 minus 1 or 1. Do that for each of these sums. I won't go through every step here. And a check on your work at this point. They better all start with the same k's and all have the same powers of x to the k here. They all do. That's a check on your work. If that's not true, go back and see what you did wrong. Now these three sums, it's all apples to apples. We can combine them into one sum. And here they are. It's all in one bracket here. And now you can apply the identity property. Everything out front here is the x to the 0 term. And what's in brackets here is the x to the k term for k equal 1 and up. So this, everything in the brackets here must equal 0 for every k from 1, 2, and up. And what's in front here must be equal 0. So this tells us that c sub 2 equals 1/4 c sub 0. In brackets can be put in recursive form this way. And notice we now have a 3-term recursive relationship. So you really want to use the 1, 0, 0, 1 trick here. So for the first particular solution, c sub 0 equals 1, c sub 1 equals 0, and c sub 2 equals 1/4 c0, and c0 is 1, so that's 4. Now start going through k's. First k is 1, equals 1. I'm solving for c sub 3. That equals minus c sub 2 times 2 times 1. Plus equals 1, so you get 0 here. Divide by 2 times 3 times 2. Go, but c2 equals 1. Oh, or c2 equals 1/4. Put that all together, there's our c sub 3 term. I'm not going to go through the rest of the arithmetic. When you do these problems, you might find that this is the part of the problem where you spend most of your time. And it's just arithmetic with fractions. It's a little tedious, and there's lots of opportunities to make sloppy errors. So try to be careful and expect to spend some time in this part of the problem. In this case, we got all non-zero terms except for the C1 term. Here it is written out through the x to the 5th power. So that is our first particular solution. For the second particular solution, we set c sub 0 equals 0, c sub 1 equals 1, and c sub 2 equals 0. As you go through all the k's, they're all equal 0. Is the solution 0? No, because c1 equals 1. That will be the only non-zero term. So this infinite sum, all you have is c sub 1, x to the 1, x. That's your whole second particular solution. So the general solution is a linear combination of particular solutions. Write the whole thing out. That would look like this. And that ends what I'm going to cover with power series solutions, ordinary differential equations.